Good morning, everyone, or good afternoon, depending on where you're sitting. It's a pleasure being here today. I have a short presentation here at the beginning to set the stage about what Xendee is doing and what we should look for when we do microgrid modeling. And then for the 35-40 minutes, I have a real demo for you, and just will build a simple microgrid case here. So when we do microgrid modeling, of course, there are a couple of steps involved here. I mean, we can go from conceptual design down to transient analysis. And my focus today is on the conceptual design and parts of the detailed design. I'm not really talking much about the one-line diagram within Xendee and also the transient analysis. So when you model or plan to build a microgrid, the first step in general is really to do this conceptual design. You want to figure out what technologies are attractive for your microgrid or project, what technologies you should consider, how much you might be saving here by installing this, how much utility costs you can save, or demand charges, whatever it is, or increase your resiliency. And typical data for this is really load profiles for a full year on an hourly basis, combined with utility information, tariff information, some technology information. Then as a result, you would get out technologies and the savings, as we mentioned. And then there's this special part within Xendee which combines a little bit the economics with the underlying distribution system modeling, which we call multi-node analysis, which really allows you to already start thinking about upgrading the distribution system while you're thinking about your economic assessment or technologies. In this detailed design, you can also assess changes over time, how this will impact your revenue. Let's say you're a microgrid as a service operator and you want to offer a contract to your clients, and of course you're interested in how changes in technology performance might impact you here. And then if you go deeper, of course, within Xendee we can do power flow analysis, quasi-static analysis, active reactive power. So it's all about the thermal system and the capacities of the cables and transformers. I'm not showing this today. And then there's also the transient analysis part that you probably have to perform when you, or someone has to perform for you when you do a microgrid. It's really about black start capabilities and so on. But that's really a very detailed analysis, and we don't have this on the Xendee platform. This is more like a support feature that we can offer to our clients. So in terms of building a microgrid and running it, we have here a special philosophy. And we think all these steps should be integrated in one platform. So when you go from conceptual design to technical design, implement a microgrid and control it, it should be guided by the same platform. And the reason for this is when you plan for a microgrid, you have certain operational behavior in mind, probably. You have certain objectives or goals, right? And they will influence your outcome of the planning for the microgrid. And if you then later on have a control and operation system which does things differently, then you have a decoupled system. And actually you cannot really guarantee that the outcome of your microgrid is really what you were planning for. And this is why everything is together in one platform here. With Xendee uses the same algorithms, and we can guide you through the conceptual design, more detailed technical design down to the control and operation. And of course, then there's also performance monitoring, which we haven't closed at the moment, which will just inform the planning tool also in terms of quality and improvements. And at the same time, with performance monitoring, of course, we can also judge on the control system here. So these are the three products, and then I go into the details of what we're doing today of Xendee. So we have a discover, design, and operate product. The discover is really, you want to figure out where you want to build a microgrid. Let's say you're a building owner, you have a couple of assets, and you want to figure out where you want to invest in a microgrid first. And then you could use this Discover tool within Xendee, which actually screens these different sites for you and then gives you color-coded information about where you have very attractive sites here. I mean, there's mostly orange and yellow. So in this project that we did, they were not really that attractive projects, but if there would be a very attractive project, then it would be green. Yellow is already somehow attractive, and then you have really less attractive ones like with orange. And then you would go deeper and design those microgrids. This is what I'm focusing on today. I will show you this in more detail. And then, of course, I already said it's about operate, where you want to control the technologies of the microgrid with the same underlying principles so that you, in quotes, somehow can guarantee a good outcome here. So basically, Xendee is a platform which allows you to reduce the design and implementation times. And we have really strong ties to the Department of Defense. So as we started the company, the biggest client actually from the beginning on was the Department of Defense. We have a lot of Army projects, installations overseas, Germany, Italy. We also work with the Navy. And of course, we have utilities here, one of our investors also, and also energy companies like Shell are working on this. Last year, we won the Edison Award in gold for critical infrastructure for the Xendee platform. And today, I really want to talk more about how to screen and do a basic design of a microgrid. And this is also what I'm showing you in the demo later on. So when you really design a microgrid, you need a couple of data points and data sets. I would say the most important data that you need actually is the load data here. And it's not that you only need the load data for the whole year. You really need it for every time step, let's say an hour for the full year, so that you can model load shifting and responses to changes in electricity rates or in performance of technologies of solar radiation. And that's most of the time already a critical point here. And not every client has this data, or maybe it's a greenfield site. So this is why we provide interfaces and databases for different climate zones and buildings so that you can get this information if you want to do screening here. The other thing is electricity rates, and of course gas rates and other fuel rates are really important drivers for microgrids and projects here. So again, here we have a lot of databases and interfaces to third parties which allow you to actually bring in almost in real time the information from your utility provider. And then of course you have to combine this for this design with some weather information, solar data, wind data. And again, this can come in through interfaces so that you don't have to deal with this. And when you plan a microgrid, you might already have some technologies on site, right? So when you set up this base case, as we call it, you need to also model the existing technologies. And when you have done this, then you think about additional constraints in the model, like is there any regulatory boundary? Is there any incentive which could help the projects? You're setting all this up also for databases and guidance systems within Xendee, and combine it here with technologies that you're interested for your microgrid. I mean, there's a whole bunch of technologies that you could consider, starting, of course, from photovoltaics to just regular batteries, but also for long-term storage like hydrogen, or on the thermal side, heat pumps might be really important. And you provide those technology options for databases, and then you give the whole model an objective. Like, do you want to do a cost reduction? Do you want to do CO2 reduction? Do you want to increase the resiliency, or a combination of this? And then with all this information, Xendee actually delivers for you what technologies you should consider to achieve your objective, how the operation should look like in the future. And that's a very important part, because on how you drive the system will influence your investment decisions or return. And then if you're already doing a more detailed analysis, you also can think about where to place the technologies on the distribution system or your local system, so that you're not burdening the system too much, or maybe you even can mitigate some issues on the cables and transformer side. So 2 slides, then I have a 3-minute movie about advanced features, which I cannot show today because they're too much, and then I go into the demo. Jay, any questions? Because I'm not seeing the chat window here, so are we good?
Yeah, Michael, no questions so far. By the way, everybody, if you do have any questions, just open up the chat and I'll be sure to pass those along.
Okay, thank you. So what you see on your screen now, this Xendee diagram or energy flow diagram, is basically how we see a project, an energy project, a microgrid. And as mentioned, we start with the load profiles here on the right-hand side. And this is not only about electricity. A microgrid is way more than just electricity, right? You have hot water needs, you have building heating, you have hydrogen needs, maybe you have refrigeration. So you want to specify these loads, as already said, maybe on an hourly basis or even sub-hourly basis for a full year, or you take it from a database. And then when you have these load profiles defined, you think backwards to the left on how you can supply those energy needs. And of course, there's a bunch of different technologies that can interact, right? I mean, we have, as already said, PV, we have heat pumps. Solar heat can actually compete for space with a PV system. We have, of course, CHP systems, which can generate electricity and heating at the same time. So there can be competition between technologies, or they can complement each other. The other thing is, of course, on the left-hand side here, we can interact with the market. We can sell back to the utility. We can have power purchase agreements and so on. But the key here is really that there's different colored arrows. In blue, fuel, natural gas, could this be, or biogas, whatever it is. In green, the electricity, red is heat, and blue is hydrogen. They change in every time step. Because let's say you have a PV system, and of course, depending on the solar radiation and the profile that you have, you might generate less electricity or more, or depending on demand charges or time of use rates or real-time pricing, you might want to purchase more, sell more back to utilities. So in every time step, the width of this arrow is going to change. And that's key, because when you assess the microgrid, it's not only about the investment capacities, it's also about these operational levels. And this is actually what we're doing in Xendee. We're assessing how we should run these technologies and how much each technology can contribute to cost savings, to CO2 savings, or increased resiliency. So in other words, in simple terms, we have investment costs and we have operational costs. And if the operational savings are really high enough to justify high investment cost, then of course you will see this technology showing up in the investment decision. And if you think about it, what you see here at the right-hand side at the bottom, this is actually a controller. Because the same methodology that we use for the planning can be used for the control scheme. And this speaks to this, what I was mentioning at the beginning, that we integrate the planning, the control into one platform. Because if you have your system implemented, you have weather forecasts that you consider, you have your load forecasts, and you combine this with real-time information of the underlying technologies, then this dispatch becomes an energy management system, which will behave like the planning tool here. Okay, so let me just fire up this movie 3 minutes, and then I will jump into the demo of the tool. This here is a real project that we did for a large campus. It's a very extended modeling approach here that we did with Xendee. It's a distributed microgrid. It has a lot of different nodes. And we had to connect all these different load pockets through cables, transformers, which we knew from the client. And then we were modeling at all these load pockets, different technology options. And the goal was actually really to figure out if we should have a more centralized PV system, or maybe the PV should go more on the roof, and how this will impact the transformers, the cables, and all this. The other goal here was also to get a fully electrified system, also on the heating side. So heat pumps were instead of the boilers, and how this will impact our costs, and also our cables and transformers. So this was the goal here of this real project. So what I'm doing here in this movie is I'm setting up the project, and as you can see, I already have these different nodes, and now I'm connecting them really with cables. And
can you make sure the quality is all the way up, by the way, Michael?
Sorry. Yep. Let me just stop this here. Yep. Okay, here we go. So Xendee can also design the transformers and cables for you. So if it realizes that there's a problem with a cable, then it will increase it at certain costs, because we have databases for cables, transformers. This is the so-called auto sizing. We have different standards, but you could also, of course, consider the cable by yourself. So what's happening here is it makes an investment decision on the technologies, but at the same time really considers the underlying physical system here. Here I'm in the PV mode, which allows you to do remote surveys. So I mean, here you can really define the available space for PV here, and then the optimization will consider it. So of course, if you say this is my space, then it cannot be bigger than what we're having here. So if we go back here, then of course I took this data from databases. Now we're going to load shapes. You can upload data on the economic side down to 15 minutes. On the power flow side, we can go to milliseconds, but that's not part of today's analysis here. So I will stop here. And when you do an analysis of a microgrid, the financial methodologies and how you want to fund the microgrid is probably going to impact your investment decision technologies that you will see. And this is why in Xendee we have different methodologies. What you're seeing here on your screen is the so-called equipment lifetime financing, which is basically an amortized capital cost approach, which is amortizing the investment cost over the lifetime of each individual equipment. And this is a really fair comparison if you want to compare technologies with different lifetimes, as you will see. There's another approach that I will show later, but now I'm going with this equipment lifetime financing in this multi-node approach, and we are interested to figure out where we should place different technologies, what technologies we should consider, and I will also show you a little bit how this will impact the cables, transformers, and the voltage levels. So we just selected the objective. I'm doing cost minimization and consider also the power flow and the losses in the cables. And here we already have the results. And as you can see, it really tells me for each node in the system how big the PV system should be to minimize my cost, and of course also the losses in the system here, right? And it goes with a centralized storage system here based on all the constraint and information that are provided. So the next thing is, I think I'm going to show you here also the dispatch. So this is what I was saying at the beginning. For every month and every day, you can see how the system should behave. Blue in this case is the utility purchase, yellow, of course, PV, and then this brownish one is the storage system. What you see nicely here is it actually does a lot of demand charge management, and it actually flattens, in this case, the purchase because of this. And at different months, it looks different. And this is actually then, if you use this technology, then the control system for the real-time system. And of course, you can check this for every node and how the energy is exchanged. Here we have voltage levels. It really checks if we have voltage problems. I already defined up and lower limits. And now I'm going into the long-term financing, which is more a net present value approach. And the net present value approach can be tricky if you have technologies with very different lifetimes. Let's say you want to compare a diesel generator with a PV system or something like this, then you might actually change your outcome, because if you have let's say a project lifetime of 20 years, then you might favor technologies which fit nicely into this project lifetime. And as you can see, the battery is gone. We have way less PV, and it's in favor now of the diesel engine. And this is because we selected a certain project length, and the lifetime of the PV would be 30 years. And with a net present value approach, you would basically, in this case, neglect all the benefits that you're getting from PV after year 20, because that's when your project would end. So this is something that you should consider when you do this analysis. Another thing is, what I'm going to show here is also multi-year analysis. The next step, when you do something like a microgrid, you're not only doing this for 1 year, you do this for multiple years. So you want to estimate the impact of performance degradation, right? Changes maybe in regulation, electricity rates, and how this will impact your investment decision. And this is the last thing before I jump into the demo. For every year, you get really how the system is evolving. And let's say you would have a microgrid as a service approach. You see that here actually in year 2030 something is happening. The gray bars are the reference case. This is your current situation if you would do nothing. And then the green bars are the investments. And it seems like in the year 2030 something is happening, because suddenly we get high operational costs. And it's, in this case, it's because we are losing, because of the end of the lifetime of the battery system, we would have to replace it, but because of the settings that I have here, it's not reinvesting in batteries, which makes the operational cost higher. So that's actually for the presentation and movie. And now I'm switching into the demo. So any questions while I'm switching here?
Nothing so far in the chat. Everyone feel free, once again, just press the button at the bottom to open up the chat box, and I can pass along any questions to Michael during the actual demo here.
Okay, so here we are in the platform. Can you see it?
Yeah, we can see your screen, Michael.
So I already prepared a case here, because building a simple case here, and if you have all the data, would be probably around 1 or 2 hours, the time which we don't have today. So I already started here a project. which already has a couple of things in it. I already put in an existing electric chiller, a boiler system, because we have also heating demand in the system. I already defined EV charging stations. I have a CHP system and a load icon, and it's a very simple microgrid. So in this case, I'm not considering the cables and transformers. This would be really a screening mode. This is a different level than what you have seen in the movie. So before I go deeper here, so let me just show you what we can do in terms of technologies. So here you see the whole set of technologies that we can consider. We also have larger technologies for the utility space, like run-of-the-river hydro power plants. We have concentrated solar power plants. We can model power purchase agreements and all that stuff. Of course, multi-energy technologies like CHP systems, heating technologies, cooling technologies, and then also, of course, hydrogen technologies. And with all the switches, I'm just turning on or off technologies I'm interested in. So I'm telling the system, hey, these are the technologies that my client would like to consider. And then based on the input data that I'm providing, it will make a decision here on the technology and provide me with cost numbers and all and so on. So the first thing here is really to get load data into the system. And as already said, I can also use a catalog system here. This is a catalog system that the National Renewable Energy Lab produced for the United States. It's separated in climate zones, so all these different colors are different climate zones. This is a project in Southern California, and I would have here a hospital building. I have certain ages here, and then I can actually get the shape for all these building types, and I can scale them up or down. So I could say, based on historic information, whatever it is, in January, we would have something like this. And like then in this way, I just can scale the system and create a kind of base case. I'm not doing this today. I'm using real-time data. The other thing is we have also utility API. So if the client has a utility API, then we can pull in the data directly from the utility here. I'm going with real-time, with real metered information. I'm just going here to the, where is it? Here we go. Electric load system. I can go down, as already said, to 50 minutes. I'm going with 1 hour, uploading it. And I'm also doing this now for cooling. This is just a CSV file, very simple. I can specify a whole set of different units here. I'm going with metered electricity for the cooling and upload this, and also now go with a thermal load, which I'm assigning the water heating, and that's basically now it. We have different views into the system. This is a more of an average view into the system, which gives you an idea about the seasonal differences for this site for weekend, and peak days. It basically comes from the idea that, of course, you have different electricity rates on weekends or weekdays. So this is also a reason why we show it like this. But in the background, of course, we have the full data set here. Let's go just to the electricity profile here. And this is the data that we have uploaded here. So now we defined electricity profiles and the heating and cooling. So now let's talk about electricity rates here. We can, of course, define electricity rates, and we can define every month as a season. If we want to do this, we have 6 time of use periods that we can define, up to 6 tiered rates. We can do this on the demand side and also on the energy side. We can upload real-time pricing data. So in a deregulated market, we could actually get the information from an interface or from the market here. What I'm doing here is I'm using my own catalog here. There's my own catalog, there's a project team catalog, there's an Xendee catalog. So that's a very important concept here. So if you use Xendee, then you can actually share data with your teammates here, and also the projects. You can build your own catalog, and then there's the Xendee maintained catalog. So in this way, you can actually build your own data sets, and no one else will see this if you want to do that. I'm going with the tariff, which is from Southern California. It's a time of use rate here. Reasonable prices with some demand charges. I could also take a generability API here, which it knows that I'm having this project in San Diego. So it's bringing in the San Diego gas and electric rates. And I could pick, let me just pick any time metered tariff here. I can specify if I have the information details, if I'm at the primary side, if details about where I'm located and so on. And then if I calculate the tariffs, then it would bring in the latest rate here, and I could use this. Takes a little bit because it has to process information. And here we see this is a tariff which has a minimum demand requirement of 500 kilowatts. Yeah, all kinds of time of usage and so on. But I already loaded my own tariff, so I'm saving this here. And we're done now with the electric rates. On the fuel side, of course, we have all kinds of different fuels. From natural gas just for boiler systems. Natural gas could be different priced for on-site generation. We have biogas, diesel, biodiesel, hydrogen, and even biomass, which is now a thing in Europe, which we could use here. I'm not changing any of these data, just keeping it as it is. And now we're switching to the technologies here. And based on the settings that I did at the beginning on what technologies I'm interested, I have a set of technologies down here. And I will insert PV and batteries and explain a little bit the other technologies that are already inserted here. So let me go first with a PV system that I will bring in as an option here, right? So I'm interested in a PV technology in the system. I have no idea how big it should be. I have no idea how much money I can save, but by providing these technologies and then later on an objective when we start the optimization, Xendee will figure this out for us. There are different ways on how we can bring technologies into the system. The first one is consider, which basically means we are considering a technology and Xendee makes a decision or the algorithm. With existing, we could model a baseline scenario, but we're not allowing it to upgrade it. With existing plus more, we could say, well, there's an existing technology already, and we want to upgrade it if it's economically attractive. And with forced and forced plus more, you can do sensitivity rounds. You can define multiple technology, multiple instances of one technology. So you could have a PV system facing south. You could have maybe a PV system on a roof, and then Xendee will make the decision on the combination of these PV locations, or maybe which one is more attractive, right? I'm going with consider. I'm modeling the inverter from the PV system in a separate way, but I'm actually taking first the PV data out from a catalog so that it's a little bit faster here. So this is just a typical number for this kind of system. And I will model the inverter separately from the PV panels. So in this case, also Xendee can design the inverter size for me, depending on the output and the loading and all that is needed here. 15 years. We can model here nonlinear cost behavior, so economies of scale. I mean, the more you purchase from a system, the cheaper it might become. So let's say a 1 kilowatt system might be way more expensive than this one. Let's say this would be 2,500. Then maybe this is, I'm just making this up, not 2,000, and then maybe we're dropping to 1,600, and then we have basically here an economies of scale. And Xendee will consider this in the optimization. I'm not doing this now. Here we have this remote survey feature that you have already seen in the movie. So if I draw this here, then it will automatically calculate for me the available PV space and consider it. I'm entering here a number. This is actually a real project that we did. So I know the number in terms of space that we have here. I'm giving a tax credit here. As you can see, we can consider a lot of incentives, and actually we just upgraded the system to reflect the latest Inflation Reduction Act measures here. I'm not modeling a macro system here. I could have also REC system on the East Coast. They use them here. Can for this one technology that I'm simulating, say, well, this is a premium panel, it should be on the roof, and if I compute this, actually will bring in the PV performance data from a unit which is only half a mile away from this site, so very accurate data. If you want to do a more detailed PV analysis, then you could upload your PV performance data from a third-party tool if you want to do this. Okay, so let's save this, and this is basically how we define a PV system. Now I could add, as said, multiple icons here with different specifications. Then Xendee will make the decision. I'm just placing this here. So the next thing is I'm adding a storage technology. Again, I'm taking this from a catalog here. And again, I already prepared here something. This is the battery here. I'm also going with consider, so very similar setup than what you have seen on the other screen. So again, I'm modeling the inverter separately from, in this case, from the energy module. A lot of different details that we can define here for batteries if you want to do this. So you can define your upper SOC limit for the battery, maybe because of warranty issues or the technology, you shouldn't charge the 100% the battery, maybe just 90%, and you can set this and the optimization will reflect this. Minimum SOC, some technologies don't like that you go below 20%, and we could enter this, right? But in an emergency, we could say, well, in an emergency, we're allowed to go maybe to 0% so that we get more energy out of this. We can also reserve certain capacity numbers and hold back. There's also temperature derating now, which allows you to model the performance of the technology, in this case, the battery, depending on the ambient temperature. There are a couple of other factors like a maximum annual cycle number for the battery, maybe of warranty contracts, or a minimum annual cycle number, maybe because of an S-chip program in California, which requires a certain number of cycling to get an incentive, right? So in this case, again, I'm giving a 26% tax credit. I'm not allowing export to the utility in this case. I'm not participating in ancillary service. I could do this if I want to do this. And I'm turning on off that we are charging from the utility. So in this case, we're setting up a system which will be completely charged for your renewable energy. So S-chip I'm turning on, and I'm saving this now. So now we define technologies. And as I said early on, if you have the data on the load profiles, on what tariffs the client is using, you can actually set up such a system very quickly, and it would take between 1 and 2 hours to set this up. So let me go through other icons that are already provided here, and then we are ready to do a couple of optimization runs and see how the results look like. So gas generators, in this case CHP, still a very important technology for microgrids. And I can define I mean, if they're running on natural gas, biogas, or hydrogen, if they are just for backup reasons in the system, or should be in the system for backup reasons, or they're just for regular operation, if it's a CHP system or standard, if we can export to the wider utility system or no. We can, of course, define efficiency numbers. We can also have temperature derating, so depending on the ambient temperature, the performance can change. Efficiency numbers can change in terms of loading. So we can define all these details if you want to do this for an engine. Down here, we have way more information. We can also consider CO2 sequestration costs here down here. I mean, if we can do this here, we can have minimum up and down time. So this same approach applies also to fuel cells. And some fuel cell technologies really don't like that you cycle them a lot. So you could specify this based on the vendor information here. Ramp rates, this is for market participation. Some technologies can ramp faster, some cannot. So these things could all be defined here. And maybe just showing you the thermal icon here. This is, I selected this is an existing boiler, which can serve 2000 kilowatt thermal, because to model the existing situation, we need some technology there. So my existing situation is I have the electric chiller, I have the boiler, and now I'm interested if a CHP system, a battery, PV system makes sense. So here with this, I just modeled the existing heat output. So let's close this, and now we're actually ready to do an optimization run here. We go to optimize, and here we have a set of different objectives, as already mentioned them in the PowerPoint presentation. We can do a cost reduction, a CO2, we can consider resilience, we can consider redundancy on the electricity and heating side, so we can have N+1, N+2, N+3 redundancy in the system. And down here, more details, like we can do a full time series optimization, meaning we use the detailed data or we use a sample data to make it faster, or for screening, we have multi-analysis and so on. So what I'm doing now is I'm doing a first run, which is just a poor cost minimization. And typically such a run takes 30 seconds. In the meantime, while this is running, I'm just switching to the results screen because I already prepared this and we save some time here. And this is how it comes back in a couple of seconds. And it always does actually a reference case and the investment case. The reference case is really the current situation, right? So it assesses that, so it took maybe a little bit, maybe 40 seconds or 50 seconds for this run now. But so we would spend $5 million at this hospital on energy costs without any of these additional technologies. So it's really the electric chiller, it's just the boiler and the electricity purchase. If we install these technologies here, we can bring the costs down by more than 52%. So that's the optimal solution here. The carbon emissions go up by 12%, and the reason for this is because we have really 3.17 megawatts of a gas generator, which runs on natural gas. And in the background, actually, we have the carbon emission data of the different utility zones. And so if we purchase electricity from the utility, we have also certain carbon content behind that. And in this case, California gets really greener these days because of renewables, so it's really harder also for CHP systems to actually be attractive in terms of carbon emissions. This is why we see this increase here, because the electricity that is generated on site for the CHP system is probably producing more carbon than purchasing the energy with this goal. We see the operational savings. We can save more than 70%. We have the lowest cost of electricity. So this is really impressive. We can bring down the cost of energy here to 5 cents per kilowatt hour, including amortized capital costs, if we would install these technologies. If we go further down here, of course, we have financial data. We can see for every month on how we are doing here compared to reference case on the left-hand side, this green blue bar. And then here we have this investment case, which is built up by investment cost, maintenance, fuel costs, and so on. Of course, return on investment, cash flow, and all this stuff. And of course, going out to 20 years, how everything looks like in terms of cash. Let me close this here. Oops, I want to actually go here. Down here, we have also a virtual utility bill here. So we really get the information about how we're doing in terms of energy costs, demand costs for every month. So, I mean, this is annual, but I could say, well, in November, these are our energy costs, demand costs, and compared to the reference case. And in this case, all the energy consumption is basically coming from a natural gas, is based on natural gas, because of this large CHP system that which is optimal if we're cost focused here. And we can also see this here if we go to this energy balance here. I mean, I would say 75% of the energy is coming from the CHP system, then this is PV, and there's a little bit coming from the utility, and this is actually why here basically all the consumption is actually natural gas and little from the utility. Here we have the dispatch that I was mentioning early on, which really shows you how the technologies are performing. And this is really an interesting result here, because we have a coupled system where we have heating and electricity. So we have a heating demand. And originally, the heating was served by the boiler system that the model is existing, but now it's using the CHP system here, this gas generator, to follow basically the heating profile. But this also means that on the electricity side, this light blue bar also means that we use it for charging the battery. So actually, we're charging the battery here in the morning before the PV system comes on, then we discharge, and then of course we use the PV again. And this is an outcome that you wouldn't see without an optimization, because a lot of people would assume, well, there's a PV system, there's a battery, and of course you use the PV to charge the battery. But this really depends on your objective. If I run this with the objective CO2 minimization, which is my next run, you will see that this changes completely. So you have to be really careful what you want to do with this microgrid. That's my point here. And this, of course, will influence your operational behavior and then, of course, your investment capacity.
Hey, Michael, we got a question as well. How is utility rate escalation accounted for in the financial modeling?
So this is the next step that I'm going to show you. We call this a multi-year analysis. This is a typical year analysis for screening, but I can just, since it comes up here, I just can go to multi-year here and can set for every year how utility rates can change, either on an average rate, or I can set this for every year based on my expectation here, right? And this is actually what I'm going to show in a little bit and how this will impact results. Okay. So let me just now do something differently. So let me switch to a CO2 minimization run. So what we are doing is now I'm saying, nope, I'm interested in CO2 reduction. Second run. And I can also provide a premium cost factor for this, meaning I'm willing to spend 20% more money than I'm spending currently just to be more environmental friendly. So that, I mean, I can say, well, let's say I don't want to be more expensive than in the current situation, okay? So the only thing I'm doing is I'm just flipping this to reduce CO2. I run this, again, this will take 30 seconds to 60 seconds. Let me just go back here so that we don't have to wait here. And it will change my technology adoption, and it will change my cost savings and my carbon savings. And now with just the changed objective, you see that the carbon savings, or in the cost objective, they went up by, I think it was 12%. Now we're reducing them by almost 26%, but at the same time, we still can reduce the cost for this site. So with a way larger PV system, with a reduced battery and CHP system, we can get to these numbers. And this is really interesting now, because again, I would think that a lot of people would think you have a larger PV system here, so you also need a larger battery system, but that's not what it is, because it figures out that a battery has charging and discharging efficiency, right? So in terms of carbon emissions, you're actually losing energy and you're creating inefficiencies and carbon emissions. This is why it's better to use the PV electricity directly. So it's actually better to oversize the PV system a little bit, use the energy directly during the day and not put it too much into the battery. This is why also the battery size is going down with a carbon reduction. But of course, as everyone would expect, also the CHP system is reduced from 3 megawatts now to 1.3 megawatts, because we put the focus on carbon reduction. And of course, this will change the operational behavior again. So one thing that I want to show you now is how we would model outages and resiliency. And then I go into a multi-year, and this would then conclude this demo here. So let's go to outages. We can model outages in a simple way, which basically means you set a certain period of time for which you expect a utility outage, and then the system will be automatically designed to sustain that outage. I'm leaving this at 3 days. I could in the exact one, I could actually specify certain ranges, and I could do sensitivities. Let's say California wildfire season. We know that probably we have more outages in September than we would expect in April, maybe. So you can play around with this and see how this would impact your adoption pattern. You can also play around with demand levels, solar levels, because maybe if there's a wildfire, then probably the solar level is not at 100%, and maybe you should be very cautious and also reduce this compared to the data that is used in the regular optimization. Demand levels, they can go up. For example, if it's a shelter, let's say it's a community and it's a shelter building, then maybe you see higher demand levels than during regular operations. You could consider all these things. But I'm going with a simple 3-day outage. Save this. And the only thing I'm doing here is I go to optimize. And in this case, I'm going back to cost reduction and I turn on resilience. That's all I'm doing, and I'm running this again. Might take more than a minute now because it has to figure out a little bit more. So let's go here to my resilience results. And it turns out that the results are basically the same that we already had in the cost saving optimization from the beginning. And the reason for this is because the system is already sized in a way only because of the cost effectiveness that it can sustain a 3-day outage. So no changes in the, and Xendee will tell you this because it actually says, well, there are no increased costs here because of this write-through capabilities, because all the technologies that we consider already from an economic perspective will guarantee that you can sustain this 3-day outage. Will probably look different if we would do a 2-week outage. Then probably we would see maybe a bigger CHP system, or probably also a bigger battery system. But this is how we would do it. So now let's switch here to the multi-year, which is the last run that I will do here. A couple of things that I have to prepare first. I just want to do a 10-year analysis so that it looks it's a little bit faster, because now we are optimizing every year here. So the multi-year, we can tell the system if it should consider upgrades in every year. So with this, we tell the system, look at every year and see if I should do something about my technologies. Maybe you're not doing this in reality because you're certainly not going back every year and upgrade your battery system, but it can be a good indicator on how technologies should evolve over time. And this is why I'm doing this here. Technology costs. So let me just see what I'm doing here. I have to change the technology cost for batteries. So I'm saying batteries will be cheaper by 5% every year. I could actually define a very detailed curve here, a nonlinear curve, and could say, well, maybe it's 10% at the beginning, then it levels off, and maybe we get to 1% or whatever. For now, I'm just using this average number here. We have also degradation on the performance of the PV system, which I'm assuming with -1%. Okay. The electric demand, I'm just assuming goes up by 3% in every year. I could actually do this again in a more detailed fashion. There's also a different mode of Xendee we call extra mode, which would allow you to actually also change the shape of your load profile. So maybe you're expecting that because of behavioral changes, your electricity profiles or heating profiles will change.
Michael, we also got another question about EV charging. Does Xendee include EV charging for vehicle to grid, which would possibly affect storage sizing, or is it only seen as a load?
So yeah, this is the only icon I didn't explain. So let me just go to this icon here. It looks very similar. What we do here is we can have a fleet management system where you can upload your expected EV charging. I modeled this as a fleet management system. And you see this down here. This is a hospital building, right? And I was modeling here the employees coming to the hospital and leaving the hospital in the evening. And then we would serve them for charging the electric vehicles. So this was just the case here. And as you can see, no one is at the hospital in the morning, then some people coming in, and then 100% of the staff is in, right? Which would constitute around 5,500 kilowatt hours, which we would have to serve them. We could charge the employees something here. I'm just saying it's for free. And then what this does is actually it will figure out how to serve this load at minimum cost of CO2 emission, depending on the objective. So in other words, there's some flexibility here, because if the optimization realizes that energy would be expensive at a certain period of time, then it will just make sure that we're not charging these cars at that time, because I only have a certain demand for the full day, and it can shift it around. The same would be true if I have excessive PV and I'm not selling it back, then it will also decide probably to charge electric vehicles. So there's a lot of flexibility, and yes, we can consider electric vehicles, if this answers the question. So let me get back to multi-year here. The last thing I think I had to do is we want to also increase the demand charge by 2% because of bottlenecks in the system. And we define all this now, save it, and now we go to optimize and take out resilience. I call this my 4th run, and I do a multi-optimization. And this will take now longer because we have this 10 years, so this might take 4 to 5 minutes. So this is why I'm switching directly again to my results here. And now you get for every year what your energy costs are, including amortized capital costs, what your CO2 emissions are, of course, net present value and all that stuff, and how your, in this case, a cost of electricity evolving over time. And as you can see, they're pretty stable here. I mean, and this is because over time we're investing in new technologies, and this is really the cool thing about this here, because we start here for the next 10 years in 21, and this yellow bar is the PV, and it stays constant. And I have a space limit here in this optimization, so it cannot really upgrade the PV system. This is why it stays constant. But at the same time, I think, I haven't really analyzed it, but because of degradation in the PV system, it seems like that the CHP system has to take on more and more capacity. And at some point, it actually flips to add more CHP. In this case, in 27, it actually decides to add 1 unit, because probably to compensate for the degradation of the PV system. In terms of capacity for the storage system, we would like to start the project with 1.2 megawatt hours, but because of the increase in demand charges, the increase in cooling and electricity loads, degradation in the battery that are modeled, we would end up actually with 3 megawatt hours of battery in year 2030. So this tells me there's a potential for a larger battery system. The question now becomes what I'm doing about this, because I can just install at the beginning here my 1.2 megawatt hours and leave it, but then probably I'm leaving some money on the table when it comes to these later years. Or I just start with this larger system at the beginning here, right? But then probably I'm spending more money because the capacity costs are really higher in 21 than we expect them in 2030. So now I can do sensitivities around this and see how this would impact my revenue stream if I would be a microgrid as a service provider, right? And I can also insert decision points here, because it tells me in 23, 25, and 29, I should reconsider something. So maybe based on additional analysis that I can do now with Xendee, maybe I say, well, in 25, I make a decision to go directly to 3,000 kilowatt hours, 3 megawatt hours, and see how this will impact my revenue stream and my cost analysis. But this is how we would use a multi-analysis to really figure out how this is changing over time. This is actually all I have for today, and we have 4 minutes left. So if there are additional questions, just let us know.
Hey, Michael, this might be a little bit more specific about maybe one project per se, but let's say you're working on a community microgrid and the city or the zoning committee, whatever, just doesn't want that many solar panels to be visible. How would you recommend powering the community, or maybe breaking up the solar panels, putting them on rooftops? So how would you approach that problem?
Well, this is exactly what I was trying to show in the movie at the beginning. I mean, you have this multi-node version. It's a community version, right? And you can actually analyze where you can place the PV system to reduce the impact for the community, or maybe also reduce the burden on the underlying distribution system. This is exactly why we have this multi-node version that I was showing in the movie, which I didn't show in the demo because it's a more complex system.
Excellent. Well, that might finish it up for our time as well. Just want to first of all thank everybody for joining us and for your interest in Xendee. I'll be putting out a recording of this likely tomorrow. You can also respond either to the email that invited you to this session or to bmiller@xendee.com, which I'll go ahead and put down in the chat as well. And you can follow up there with specific questions about your organizational goals or your use case, and also get yourself started on the free trial. So once again, thank you everybody for your time. As far as next steps, once again, we invite you to reach out, start that free trial, explore what we've learned today, and really, test it out in Xendee and see how it works for you and your organizational goals. So thank you again, everyone. Thank you very much for your time. Thank you, Michael, and we'll talk to you all soon. Bye.
Thank you.